Hello, this is a paper walkthrough for Paper 1 Chemistry, November 2021. Right, let's take a look at this question about the periodic table. It's going to go through lots of topic 1 stuff. So Mendeleev's version is here, and it says which group of elements had not been discovered when Mendeleev's version of the periodic table was published. There is very little clue from what is present in this table. It's just one to learn. There was no group 0. Next question. Which model of the atom represents the plum pudding? So if we remember that we have a ball of positive charge, there it is, with electrons embedded all about right through the volume of it, then we've got B there. And which model resulted from Chadwick's experimental work? We've got, it has to have a neutron. So we should have A there. Now we're asking about isotopes, so we've got an actual definition here, so it must be the same number of protons and different number of neutrons. There are alternative definitions, but the question is saying refer to subatomic particles, so that's what I'm doing. And we've got to calculate the relative atomic mass of potassium. So we've got the mass number of each one, 39 and 41, and we've got the percentage abundance. So 39 is a lot more abundant. There's a lot more 39 than there is 41. So we're expecting the number to be close to 39, but slightly above 39. And so let's use our working method that we have the mass times the abundance. And the abundance is a percentage, so we're going to need to divide everything by 100 when we've finished. Plus the next mass. So remember from previous past papers, you don't necessarily have to have just 2 isotopes. Neon, there's a neon question with 3 isotopes in it. And it's asking for 1 decimal place. It's not asking for significant figures, it's asking for 1 decimal place, so we can be very good about that and just put 39.1. There are no units. Okay then, on to a new topic of acids and chemical reactions. Acids reacting to produce salts, so that means that you've got metal which has replaced the hydrogen ions inside an acid. Universal indicator is added to water and then nitric acid is added to the mixture. So we've got universal indicator, which is red in acids and blue or purple in alkali and green in the middle. So nitric acid is added to a mixture of universal indicator and water. It should turn from green to red. And then what happens to the pH of the water? It should go down because low pH numbers to do with acids. And the state symbol for nitric acid, so it's dissolved in water, and we're not allowed to put any capital letters, lowercase a and q. That question will be marked by a non-expert marker. Okay, now on to the chemical reactions that you know from your required practical. So zinc carbonate is reacting with nitric acid, and there's a word equation given to you. So this is our salt. This is proof that neutralization has occurred. Okay, and when you read the next question, you may think that they've given you the answer already in a way, because they've put white solid and colourless solution here. So 2 observations that we've made when zinc carbonate is added to nitric acid. So the first one is that we've got a gas produced here, so we can put fizzing. Gas produced is not an observation. Fizzing is an observation because it's what you see and hear. Gas produced is an explanation. Okay, and then you can see afterwards the fizzing, then there you can say that the solid disappears. Yes, there may be some left, but it's definitely going to disappear because you end up with a solution and there's no solids on the right hand side of the equation. The formula of the zinc ion is zinc Zn2 plus. The formula of the nitrite ion is NO3 minus, and I'm sorry, when I transferred this to PowerPoint, the minus sign got in the wrong place. What is the formula for zinc nitrate? So we have to balance the charges. So we have 2 plus some minuses must equal 0. We have to have a neutral compound. So we're going to need 2 nitrate ions. Acids react with insoluble metal oxides to produce salts. Plan a method to produce a pure, dry sample of the soluble salt copper chloride from an acid and a metal oxide. Okay, so we're going to use complete names for everything that we use. We are never going to just put, oh, we need copper. We're always going to call it copper oxide. And the rest of the salt name comes from the acid, so it must be hydrochloric acid. Check your spelling. Okay, and to tackle a question like this, it may be a good idea to draw a diagram first. And so you can say that making salts always comes in 4 stages. So we're going to add excess base. That's our first step. The second step is that we're going to filter away the excess base. We're going to collect the solution, which should be only salt plus water now, because if you used excess base, then all the acids should have reacted by now. Step 3, we're going to evaporate, and we're going to use a water bath to do careful evaporation until only you've got the saturated solution, no further than that for safety reasons. That's your salt plus water. And the 4th stage is to leave your saturated solution to cool down so that crystals can form from your saturated solution. Okay, so that's overnight. And it's got to be cooled. Okay. So to write the method, you can see on the right hand side what the key aspects of the method are, but let's just remind ourselves what are the very important things to do. So we've got to make sure that there is excess copper oxide. Don't just call it copper, don't just call it oxide, excess copper oxide. And how do you know? You add until no more dissolves. And also, because it's copper oxide, when we did this for our required practical, we heated at this stage as well. But actually, you might not want to use direct heat for your acid, so safe heating, e.g. water bath. Whenever you heat, that's fine. When you've got your residue left behind, you can say what the residue is. Unreacted copper oxide. And then how long do you heat it? So evaporate until solution is saturated. So that means that crystals start to form. On the edge or on a glass rod, dipped in the solution. Okay, and then the final key point, these are just the key points. You can see the mark scheme right beside, so I'm not going to do the whole writing here, but just the key points. And then the last one is evaporating is heating. But crystallizing is cooling. So both of those are important. Okay, and as you can see in the mark scheme here, it says for level 3, the correct chemicals must have been selected. So lots of people might not say what the acid was or something like that, and then restrict themselves to 4 out of 6 marks. Okay, now another required practical straight after, one after another. So this time, the way that this has been structured, they're not asking you for the method, that would be incredibly boring, but what they are asking you to do is to just evaluate somebody else's investigation. So let's just read through the investigation and just see whether or not there are some improvements that can be made straight away. So we're measuring energy change. So we are definitely measuring with a thermometer. So that looks pretty positive. Yep, got a thermometer there. Okay. Oh, it's a glass beaker. Haven't we done this with a polystyrene cup? Wouldn't that be better? With a lid. Because we've got some heat losses going on. Ammonium nitrate. So that's our salt. Let's have a look. We've got plenty of water. Looks about right. 100 centimetre cube, 10 grams of ammonium nitrate. That should be reasonable for level of accuracy. But let's just see if we think we can improve on that at all. Stir it once? No way. That is never going to dissolve. Okay. Measure the temperature of the solution every minute for 7 minutes. Seems okay. No, you need to stir until dissolved. Okay, and right, so the dependent variable, the thing that we're measuring is the temperature. Okay, so let's see if we have got some improvements that we can make. So change to polystyrene cup. And add a lid is a separate marking point. Hooray! Change to polystyrene cup for better insulation. Prevent heat loss by adding a lid. Stir until dissolved, if possible. Okay, and then the absolute classic for making the results more accurate is on the mark scheme as well. Okay, and this is always one to remember. So repeating and discarding anomalies and calculate a mean. Okay, and then it's got some other things that it's saying, like using a smaller volume of water or a larger mass of ammonium nitrate so that you get a bigger temperature rise, basically. More accurate balance, digital thermometer, just be careful. Those are actually asking, those are to do with precision as well. So change errors in the method first before you start cracking into trying to find better levels of measuring apparatus. Okay, so it's got some results. It says that it measured every minute for 7 minutes. So how did the line of best fit look like that? Let me just check. Measure the temperature of the solution every minute for 7 minutes, and then you get a line of best fit where it's changing direction at 1 minute and 30 seconds. I don't understand. What is going on? Luckily for us, all we need to do is just to explain the results that we can see in the graph. So if it says explain, we're going to describe and explain every single time. That's what explain means, describe and explain, state and explain. Just don't forget to explain. But if you don't state or describe, then you're going to lose marks. Because look at the mark scheme. The first one is temperature decreases. Until 90 seconds, 1.5 minutes. Okay, then temperature increases steadily. Okay, so we're talking about heat changes, and you know from our topic that we can use heat transfer in and out. Okay, so heat transfer from the solution to the chemical system. Endothermic change. When ammonium nitrate dissolved. Then the solution got warmer again. As it equilibrated with the surroundings. In other words, heat was transferred to the system, to the solution. From the warmer surroundings. Okay. .4, a reaction profile for an exothermic reaction. Okay, so just be careful. We've got heat coming out to the surroundings, leaves the chemical system, goes to the surroundings. So the energy level of the reactants and the product, so let's label reactants. Okay, and then we should have the overall energy change to the product, so the products have less energy than the reactants. Let's make sure my arrow goes right from one line to the other, and I'm going to label it overall energy change. I'm going to just label it delta H, but I'll also put that here so that the examiner knows. Okay, and products. And the activation energy, so that we're going to show a hump, but that's not the activation energy. That's just the path in energy taken from reactants to products as the reaction progresses. So I now need to draw an arrow up, and that's the activation energy, that arrow, from the reactants to the top of the hump. Okay. So the marks, it says allow curve to start finish anywhere along reactants and products lines, and as you can see in the mark scheme, they've labelled the activation energy on some continuation dotted lines there, which is also fine, of course. Okay, question 4. Some structure and bonding for us now. Carbon can exist in a number of different structures. The first fullerene was Buckminster fullerene. What is the formula? C60. Graphite is a form of carbon. Explain why graphite conducts electricity. So we're going to say that it has delocalized electrons between the layers. Carry charge through the structure. Okay, and we have the different sized atoms argument here for steel is being harder than iron, so it's an alloy, so we're just going to say that it's a mixture of metals first. Is a mixture of metals with different sized atoms. the layers of atoms are distorted, so they cannot slide as easily when a force is applied. Which is why it's harder. Okay then, so now a calculation. Iron is alloyed with carbon and other metals to make stainless steel. And a stainless steel fork contains 71.92% iron. Table 2 shows the mass of each element in the fork. So we have unknown mass for iron, we have carbon, chromium and nickel, and it says calculate the mass of iron in the fork. Okay, so we've got a percentage for one thing that we don't know what its mass is, and we can work out the remaining percentage. So 100 minus 71.92 equals 28.08%, and the total mass of 28.08% equals the mass of C, Cr and Ni added together equals 16.29 grams. So if you didn't have a calculator on you, you could still try and work it out by saying that 16.29 is 1% would be that divided by 28, but you're going to have your calculator with you in the exam. So we are just going to just say what the mass of the iron is. So mass of the fork must be 16.29 divided by 0.2808, and mass of iron equals 0.7192 times that answer. Equals 41.72. Thank you. Okay, question 5, electrolysis. Hydrogen gas and chlorine gas are produced when sodium chloride solution is electrolyzed. So let's just make sure that we know what ions are going to be present. It's sodium chloride solution. So we have Na plus in there, we have Cl minus in there, we have H plus in there, and we have OH minus in there. Okay, the half equation for the reaction at the negative electrode is to make one molecule of hydrogen gas from 2 hydrogen ions and 2 electrons. And that is reduction because electrons are gained. Okay, so the answer is not electrolysis, because that would mean that you'd have to have 2 electrode reactions going on at the same time. So this is what you could call half a reaction, so the reduction half of a redox reaction. So we've got to be able to complete half equations for these, and you've got to memorise all of your water reduction and hydroxide ions and hydrogen ions reductions as well. So our half reaction here, we have to make some chlorine gas, and we've got to pull off electrons to do so, and we have to do that twice to make one molecule. So hydrogen gas and oxygen gas are produced when sodium sulfate solution is electrolyzed. So this is yet another required practical, and it's asking you about the oxygen gas being produced. So we could give an equation here, which would be, which isn't even given on the mark scheme, it should be. So let's just write it just at the bottom here so that you know what it is. we go. So we've just got to explain this in words now. So we've got hydroxide ions are attracted to the electrode. Hydroxide ions from water molecules. That dissociate. And again, use an equation. And you can use an equilibrium if you want as well. Okay, so the dissociate to form hydroxide ions from water are attracted to the positive electrode. And lose electrons. Okay, and then for other mark schemes, they're going to be talking about other stuff. For example, two oxygen atoms combine. So I'm just recalling questions about aluminium manufacture and things like that. So two oxygens can combine to form a molecule of O2. There we go. I think that should be enough for any mark scheme now. Okay, question 6, we've got a conservation of mass question, so we're going to do some calculations about moles. A student investigated the change in mass when 0.12 grams of magnesium was heated in air. So here is the magnesium, and it's going to form magnesium oxide. Okay, and you're going to weigh things before and after. So we've got 0.12 grams of magnesium reacting to produce 0.20 grams of magnesium oxide, and the number of moles that have been produced must be the number of moles of oxygen gas that reacted must be the number of moles that you get in that difference between the two masses, because it's the law of conservation of mass. So you've got 0.20 grams of this, and you've got 0.12 grams of this. The rest of the mass must be oxygen. Mass of oxygen equals 0.20, take away 0.12. 0.08 grams, so moles of oxygen, gas equals mass divided by MR, and the MR is 32. Okay, so the most common mistake would be to put 0.08 over 16. Sorry, I haven't put it on the answer line. Let's just check that I don't get it. I don't make a typo, as it were, at that point, because if I put it correctly here and then wrong on the answer line, it would be wrong. Okay, so a short calculation there, and now we've got to check on the method. The student repeated the experiment without a lid on the crucible. Suggest why the magnesium oxide mass would be different without a lid. Okay, so magnesium oxide escaped. So mass measured at end was lower. Okay, copper reacts. It's a very, very light ashy powder that you get, so that's why it escapes. Copper reacts with oxygen to produce copper oxide. 63.5 grams of copper, that's 1 mole. Produces 79.5 grams of copper oxide, that's also 1 mole. Okay, calculate the mass of copper oxide produced when 0.50 grams of copper reacts with oxygen. and give your answer to 3 significant figures. So there's a shortcut way of doing this. We're just going to take the ratio of these. So you could go for 0.50 grams of copper and do the whole method. So we can do that quickly. So moles of copper equals 0.50 over 63.5, and so moles of copper oxide equals moles of copper. Okay, but there is a much quicker method to do this, and I expect you can see already that we're just going to take a ratio of these. So you can say the mass of the copper oxide equals 79.5 times 0.50 over 63.5. But if you take a look at the working here, all they've done is they've just taken a ratio, 79.5 grams over 63.5 grams, and that's completely legitimate for a question like this. But we've gone the moles way so that we can do the more complicated questions where we have a ratio, because 1 mole of copper oxide doesn't in this answer just came from 1 mole of copper, but it's not always going to be like that. So this is our longer method for when we have a different reaction with different ratio of moles, but there is also this shortcut that you can use right here. Okay, so here is another way of asking a moles question. It's more unusual. It's sometimes called empirical formula. But all we're just going to do is we're just going to make sure that we take a ratio of these, the number of moles, and then we can work out what the formula will be. So if we've got 0.015 moles of iron and it's reacting with 0.010 moles of oxygen gas, that's 1 Fe reacts with 1 Fe, no, let's just change it, make it nice and easy. So we've got 15 Fe would react with 10 O2. So cancel that down, 3 of them reacts with 2 of them, but that's 2 O2s. So 3 Fe reacts with 4O. So the formula must be Fe, small numbers, 3 Fe3O4. And the balanced symbol equation for it now, so we've got 3 Fe's plus 2 O2s, just like we did in our working, makes Fe3O4. There you go, not too bad. Question 7. It's asking us about these things. Alkanes. Methane, ethane, propane and butane all react with oxygen to produce carbon dioxide and water combustion. Suggest why a mixture of methane and oxygen does not react at room temperature. Answer in terms of particles. So that would mean even if they collided, they don't react, because methane and oxygen are gases. So gases, so they will collide. But unsuccessfully. At room temperature, they don't have the activation energy. The particles, that is. Oh, do not have, so have less than the activation energy is a best to put it. Table 3, the energy released when methane, ethane and propane react with oxygen to produce carbon dioxide and water. Predict the energy released when butane reacts with oxygen. So as you know, we've got CH4, C2H6 and C3H8. We know that a homologous series increases by CH2 each time. So we're looking for numbers to be a good steady increase, and so we should have that we can take the difference between these and find it's the same each time, and indeed it is. So we can jump straight to the answer there, 2120. Okay, and now we've got a bond energy calculation where we are going to need to calculate an individual bond's energy. So we can write some working in here to make sure that we don't miss out any bonds at all as we're writing down our working. And we're going to say bonds broken. And we're going to say bonds formed. In fact, let's put them over the other side so that it matches up to the equation. And then lower down, what we're going to do is we're going to write the formula. So delta H equals the sum of the bonds broken. Take away the sum of the bonds formed. And then we're going to substitute in the numbers, and then we're going to find out what X is. Okay, so looking at the bonds broken side, we have 2cc, so we're going to put 2x. We have 1, 2, 3, 4, 5, 6, 7, 8 CH. So 8 times 410. And we have 5 O double bond O equals 5 times 500. So adding all of those together, we get 2x plus 3280 5780 kilojoules per mole. And then bonds formed, we've got 3 times 2 times C double bond O, 6 times 740. And we've got 4 times 2 times OH equals 8 times 460. Altogether 8120. Okay, now because I haven't forgotten this, I'm going to get all 5 marks, but you can end up with just 2 marks if you forget to write this part. So really, really important to make sure that you're including this. And you can only get 3 marks if you don't include X somewhere in the working here. So make sure you show X at this point. Don't just write 5780 or anything like that. Show X at that point. Okay. So then, what is the total? In this reaction, the energy released when forming new bonds is 1,640 kilojoules per mole greater than the energy needed. Well, that is lovely of them to tell you it like that rather than the overall energy change equals, but we do understand, they're trying to test that we understand. So that is going to be minus 1640, because you get more energy released than you took in to break bonds. So minus 1640 equals 2x plus 5780 minus 8120. X is 350. Thank you very much.